Welcome to the Deep Dive. Today, we're tackling a really interesting challenge that engineers face all the time: uncertainty.
Hmm.
When you think about designing anything, a bridge, a stadium, you're dealing with materials that vary, loads that fluctuate,
Hmm.
imperfections. How do engineers even factor all that in?
Well, that's really the core of what we're looking at today. A common way is using intervals, basically setting a range, a lower and upper limit, for things like material strength or maybe the weight a structure carries.
Okay.
It's not that we don't know the value, just that we know it's bounded, you
Right,
know?
defining a zone of possibility. And in structural engineering, the finite element method is sort of the standard tool, yeah, breaking things down into smaller bits for analysis.
Exactly, like detailed Lego bricks, as you said. Our focus today is on applying these uncertainty intervals within that method interval analysis.
Gotcha.
But the sources we looked at, they actually push beyond that standard interval analysis.
So,
Well, what's really interesting here is an approach that gets that uncertainty isn't always independent for every single part.
okay.
Think about, say, a batch of steel used for several beams, all those beams. They'll share some underlying uncertainty just from coming from that specific batch.
Makes sense.
But then each individual beam might also have its own little variations, manufacturing, installation, that kind of thing.
Ah, okay. So multiple levels.
Precisely. And this newer method, they call it multi-level multiplicative interval uncertainty. It lets us account for both that shared group level uncertainty and the unique element level stuff.
That clicks intuitively. If parts come from the same source, their properties are probably linked somehow.
Mm-hmm.
Treating them as totally separate seems like it might, distort the picture, maybe make the predicted range too wide.
Exactly. You've hit on a key challenge in interval analysis, these dependency issues.
Dependency issues.
Right. If you just plug independent intervals into the equations, you can end up predicting structural behavior that's, well, much wider, much more uncertain than what's physically possible.
Why does that happen?
It's partly just how interval math works, especially if the same uncertain variable shows up multiple times in an equation. It can compound and lead to overestimation.
Overestimation meaning the range looks bigger than it really is.
Okay.
Okay, so the mission for this deep dive is to unpack how this multi-level multiplicative method tries to give us more, let's say, realistic and reliable predictions by handling these uncertainty complexities better.
Sounds good.
So let's start with why the simpler ways of using interval analysis can sometimes fall short. What are the main bumps in the road with basic interval analysis?
Well, the basic idea is simple enough. Like, a material's stiffness isn't just one number. It's a range, say, 200 to 220 gigapascals, an interval.
Okay.
And then you do math on those ranges. Adding two uncertain things, you add the low ends for the new low end, add the high ends for the new high end.
Seems logical. Where does it get tricky?
The problem pops up because some algebra rules we take for granted with single numbers, they don't quite work the same way with intervals.
Give me example.
The classic one is the distributive law. A times B plus C equals A times B plus A times C. That's solid for regular numbers.
Right.
But with intervals, if you have interval A times the sum of intervals B and C, the result is inside the sum of A times B and A times C, but it's not always equal. It can be narrower.
Ah, I see. And that difference is where the overestimation comes from.
That's a big part of it, yeah. That potential widening of the interval.
So this overestimation, our calculated range, being wider than the true possibilities.
Yeah.
Why is that such a big deal in structural analysis specifically?
A major reason comes down to how we set up the math, the parameterization. Remember the Lego bricks?
Finite elements, yeah.
Each element has properties like stiffness. Stiffness depends on the material Young's modulus and its shape cross-sectional area. Now, for one specific element, those properties are physically linked. Its actual modulus and area are single values, even if they're uncertain values within their intervals.
Right.
If we build our equations using interval math and treat the modulus interval and the area interval as totally separate things every time they appear in the stiffness calculations for that element, well, we're breaking that physical link.
Oh, I think I get it. You're allowing combinations in the math, like minimum modulus with maximum area in one term and maximum modulus with minimum area in another term for the same element, which couldn't actually happen simultaneously in reality.
Exactly. You're allowing scenarios that are physically impossible for that single component. So getting the proper parameterization, setting up the math to respect those internal dependencies is crucial.
Otherwise, you get unrealistic results.
Right. Incorrect parameterization is a major source of overestimation in basic interval analysis. Figuring that out was a key step.
Okay, so basic interval analysis has limits, especially with dependencies leading to these wide predictions. When engineers face these interval equations, what methods have they typically used to solve them?
Right, so over the years, several techniques popped up for these interval linear systems. One big group is optimization methods.
Okay.
The idea there is to hunt for the absolute minimum and maximum possible response, like how much a point deflects, maybe by tweaking all the uncertain parameters within their intervals. You often use standard analysis tools repeatedly.
It sounds computationally heavy.
Oh, it can be. Finding those absolute extremes, it's often what we call NP hard,
Meaning,
meaning the computing time can explode, maybe exponentially, as you add more uncertain parameters. Plus, you usually optimize for just one output at a time, like one displacement. To get the full picture, you might need many runs.
and you might not even be sure you found the absolute worst case.
Exactly. Depending on the algorithm, there's often no guarantee you found the true bounds.
Okay, so optimization, potentially slow, maybe not guaranteed. What else?
Another very common one is Monte Carlo methods.
Random sampling.
Pretty much. You treat each uncertain parameters interval as, say, a uniform distribution. Any value inside is equally likely. Then you run tons of simulations.
How many tons?
Thousands, maybe millions. Each time, you randomly pick values for everything uncertain and run a standard analysis.
So you build up a statistical picture.
You do, but the catch is, it doesn't guarantee you've covered all possibilities. There's always a chance you miss the one specific combination that gives the true max or min response, especially with many variables.
And again, potentially lots of computation.
Can be, yes, to get good statistics.
All right, optimization, Monte Carlo, any others?
Then you've got perturbation methods. These assume the uncertainties are relatively small changes around some average or nominal value.
Okay.
They use math tools, like Taylor series, to approximate how these small input changes affect the output, often just looking at first or second order effects.
So they simplify by assuming small uncertainty.
Basically, yes, which means they don't give guaranteed bounds either. They're more for getting a quick feel for sensitivity to small variations.
Makes sense. Anything else in the toolbox?
Yes. Sensitivity methods, sometimes called endpoint methods. The idea here is that the extreme responses often happen when the uncertain inputs are at their extremes, the ends of their intervals.
So just check the corners, basically.
In the simplest brute force way, yeah. But if you have uncertain parameters, each with two endpoints, that's 2 to the power of n combination.
Yeah, that grows incredibly fast.
It really does. Impractical for complex models. But smarter sensitivity techniques exist to try and cut down the checks. And interestingly,
Yeah.
for some very specific problem types, like when an uncertain parameter just scales a part of the system in a simple way, mathematically, like multiplying a rank 1 matrix, it turns out the endpoint checks do give the exact answer.
Oh, interesting. So sometimes the corners are enough.
In specific cases, yes. And finally, the approach relevant here, fixed point methods. These are grounded in math theorems that can guarantee finding bounds on interval equation solutions. They work iteratively.
Iteratively. How?
You start with a guess for the solution interval. Then you repeatedly apply some equations to refine that interval, making it tighter, until it stabilizes, basically, until further repeats don't change it much.
So you zero in on the solution range.
Exactly. And the big plus. Fixed point methods do give guaranteed enclosures of the true solution set.
Guaranteed. That sounds valuable.
It is. They can also help gauge how much overestimation other methods might have, and they often give you the solution intervals for all the unknowns at once, not just one at a time.
Okay. Quite a range of methods, each with pros and cons.
Yeah.
Now let's dive into this new multi-level multiplicative approach. What's the core concept?
The key idea is representing uncertainty not just as one interval, but as a product of intervals.
A product.
Yeah, it lets us model different layers of dependency more realistically. Back to the steel batch example. The uncertainty tied to the whole batch affecting all elements made from it, that's one interval. Then the extra local uncertainty for each specific element, maybe slight dimension differences, that's another interval. The total uncertainty for that element's property, it's the product of those two intervals.
Okay, so like overall uncertainty equals shared uncertainty times individual uncertainty.
Kind of like that, yeah. And mathematically, this product of intervals can be broken down, decomposed into parts that are fixed numbers and parts that are centered intervals symmetric around 0.
And why do that decomposition?
It's a crucial step for setting up the specific fixed point math used to solve the structural analysis equations that result from this representation.
How does this fit into the standard structural equations like Kufi?
Right. So with intervals, that becomes Ki Ui equals Fi. Ki is the interval stiffness matrix, Ui is the interval displacement vector we want, Fi is the interval load vector. This multi-level method uses a specific way to decompose both Ki and Fi. The aim is to pull apart the definite parts from the interval parts carefully, managing those dependencies we talked about, to ultimately cut down on the overestimation.
So the decomposition helps manage dependencies. Then how do you actually find the displacement range, UI?
The decomposition leads to a fixed point equation for UI. But to clamp down even more on the intervals widening during the iterative solution, they introduce an extra variable, let's call it VI.
An auxiliary variable.
Yeah, it's mathematically linked to the displacements, UI, but working with VI helps avoid repeatedly crunching terms with the UI in every iteration step, which is something that can inflate the interval width.
Ah, clever. So you iterate on this related variable, VI, to keep things tighter.
That's the idea. Then you use an iterative process, a specific calculation sequence, EQ11 in the source. You start with the guess for VI, update it based on the last estimate and the problem's uncertainties, and repeat until it converges, until VI settles into a stable interval. In the examples, this happened fast, like fewer than 10 loops usually.
Wow.
And because of how interval math works and how the scheme is built, it guarantees that the final VI interval encloses the true solution range for VI. Once you have that converged V.
But then you can find the displacement interval UI from it.
Exactly.
Yeah.
You calculate the corresponding UI interval directly.
So recap. Multi-level uncertainty via products of intervals, decomposition to handle dependencies, fixed point iteration with an auxiliary variable for guaranteed bounds. That's the method.
That's the essence of it, yeah.
Let's see how it played out. What did the examples show?
Okay, so they had three main examples. First was pretty simple. A 4-bar truss, just 4 interconnected bars.
Okay, a basic test case.
Right. They use it to show clearly how the method reacts to different uncertainty assumptions. Like, what if all 4 bars have independent uncertainty? What if they all belong to one group, sharing uncertainty?
And the multi-level case.
And then the multi-level case. Maybe 2 bars form one group with shared uncertainty, the other 2 form another group, plus each bar still has its own individual bit of uncertainty on top.
Okay, covering the bases, what came out of that?
The results were really telling. The widest displacement range, that happened when they assumed everything was independent, just as you'd expect, maybe.
Right, that allows for the most extreme combinations.
Exactly. The narrowest range was when all the uncertainty was fully dependent, one big group.
Also makes sense.
But the key finding, the real aha moment, was the multi-level case. When they grouped the bars with shared uncertainty, the resulting displacement uncertainty fell right between those two extremes.
So more realistic modeling led to tighter, more specific predictions.
Precisely. It showed that capturing those correlations lets you narrow down the possibilities compared to just assuming total independence, which can be overly conservative.
That's a really important result, and computationally.
The fixed point algorithm handled all these cases really quickly, efficiently, and crucially, the results it gave always contained the exact solutions.
How do they know the exact solutions?
They calculated them the hard way, checking every single combination of endpoints for all the uncertain parameters. Very time-consuming, but it gives a benchmark.
Gotcha. And how close was the fixed point result to that exact but hard-to-get solution?
Very close. They reported only about 5% overestimation in the width of the solution intervals compared to the exact ones.
Wow. So more realistic, computationally practical, and pretty accurate with guaranteed bounds. What about something more complex?
Example 2 was a 15-bar truss. More intricate, statically indeterminate.
Okay, scaling up.
Yeah. And here, they didn't keep the overall uncertainty level fixed between cases. Unlike the first example, they looked at uncertainty just in the loads,
Okay.
then independent uncertainty in both loads and all 15 bars' material properties.
Right.
And finally, introducing 1 or 2 independent groups of bars sharing material uncertainty alongside the individual bar and load uncertainties.
What did they find here?
Well, first off, when only the loads were uncertain, the fixed point interval solution matched the exact combinatorial solution perfectly. 0 overestimation.
Interesting.
But when they added material uncertainty for the bars and load uncertainty, the displacement intervals got wider than the exact solution, showing some overestimation as expected.
Okay.
But here's the key bit. When they then added the group uncertainty modeling those shared dependencies, the increase in that overestimation, compared to the case where all elements were treated independently, was tiny. really slight.
So adding the more realistic group dependency didn't really hurt the accuracy much at all.
Exactly. It reinforces the idea that you can capture these important group effects without a significant hit to the precision of the bounds.
That's encouraging for applying it to real structures.
Definitely. And they also noted something neat about the internal forces in some bars. In this truss, some bar forces are just determined by overall equilibrium, so they shouldn't depend on the material properties, and the interval finite element method they used. It correctly showed zero uncertainty width for those specific forces, capturing that known structural behavior.
That's a great sanity check. It shows the method respects the underlying physics. What about even bigger structures?
Right. The third set of examples used a series of cross-braced truss structures, getting bigger and bigger. The largest was a 10-bay, 10-story truss with, get this, 434 independent interval parameters.
Whoa. Okay, now we're talking complexity. What was the goal here?
Benchmarking. They compared their fixed point method against other techniques people use: sensitivity analysis, particle swarm optimization, genetic algorithms focusing on the displacement of one specific point.
How did it stack up?
In terms of the predicted displacement ranges, all the methods gave results that were pretty close to each other. But the huge difference was only the fixed point method provided the guaranteed enclosure. The other methods, especially on these complex problems, couldn't offer that same certainty. The true max or min might actually lie outside their predicted range.
So, confidence versus approximation. The fixed point method gives you the guarantee.
That's the critical distinction. Plus, it was computationally efficient, especially for these big problems.
Right, because the exact combinatorial check becomes impossible.
Completely impossible. And they pointed out their reported time for the fixed point method was to get all the structural responses, displacements, forces, everything, while the times for the other methods were often just for that one displacement variable they were comparing.
That really drives home the efficiency point for practical engineering. Okay, let's try and wrap this up. What's the main takeaway from this deep dive on the multi-level multiplicative interval uncertainty method?
I think the key message is that this approach, especially solved with that fixed point iteration, is a really valuable development for handling uncertainty in structural analysis. By letting us model dependencies at different levels, like shared uncertainty in a material batch, it paints a more realistic picture of how real structures behave.
Leading to better predictions.
Potentially, yes. Narrower, more useful bounds compared to just assuming everything's independent. And critically, it gives guaranteed bounds on the response, and it's computationally feasible even for large, complex systems where other exact methods just aren't practical.
And it might apply beyond linear problems, too.
Yeah, the research hinted it could be extended to nonlinear material behavior, which opens up even more applications down the line.
That's genuinely fascinating.
Yeah.
It really highlights the depth of thinking needed to ensure safety and reliability, doesn't it? It's not just about knowing there's uncertainty, but really digging into how that uncertainty is structured, how things are linked.
Absolutely.
It does make you think,
Yeah.
if modeling these multi-level dependencies is so useful in engineering, where else could that thinking apply?
Here.
Could you use similar ideas for, say, climate models or complex economic systems? Understanding those layers of shared versus individual uncertainty.
That's a provocative thought. Lots of complex systems out there with interacting uncertainties.
Definitely something to chew on. Thanks so much for breaking this down with me today.
My pleasure. It was interesting stuff.